Hi, welcome to our paper on X3D and glTF model differencing for conversions, comparison, and conformance testing. X3D4 now includes full capabilities for glTF 2.0 compatibility, providing physically based rendering and lighting techniques. We want to ensure that X3D4 players match exactly to each other and glTF reference images in every single use case now and in the future. The main point of our paper is to walk through different differencing methods that are useful and helping find out why models look different. There are several different types of differencing techniques that we use. The first is plain text differencing. It allows us to find the differences between two models that are represented by just plain text documents. The second is structured text differencing, such as the differencing between two XML documents. 2D rendering differences is most familiar to most people, where we compare rendered images and use differencing techniques on them. There's conversion differencing, where we look at the same model that's been rendered with a glTF render and converted into an X3D rendered model and do a comparison that way. And that's been very useful for helping us identify issues in specification and conformance. 3D differencing looks at how a model's structure may change over time, whether that's the mesh through some reduction or compression techniques may alter the underlying structure. And another type of differencing is in animation, where certain keyframes are selected and then we choose the 2D differencing techniques. So canonicalization is important because in plain text documents and even some of the in some of the structured formats, there's not always consistent ordering between data elements or representation of those data elements. So getting those same peer level sets of information ordered in a way that's consistent helps us do differencing comparisons. So structured text differencing is quite mature. Many folks who write application code use this all the time to understand where there are insertions or deletions and how a particular code base or structure changes over time. And so we've adopted this to do comparison for the structured types of documents, mainly XML-based documents. And this simple visual illustration shows a change in a line, deletion and insertion using a color scheme. It makes it very apparent where a certain change occurred, and if that change caused a difference in the object models, then we're able to find out where and ultimately what and why it changed. So in 2D rendering differencing, we can look at sets of things like the particular reflection mode of a surface property and see how those changes to an implementation, a rendering implementation, may cause differencing over time in a set of features. So this multi-textured teapot example is a useful example that we use to find where there were additions needed to the X3D specification, and it was helpful for that for us. One thing that we found very helpful is the glTF 2.0 samples, and we scripted the automation of the conversion of those to X3D, and then we also scripted the rendering of those models for generating comparison images. So the example you see is one in particular that is pretty common in helping shake out where there are differences in the specification or where there are differences in the implementation of the specification. And this sort of use case is the latter, and it makes it apparent when maybe a certain feature isn't implemented yet in a particular X3D render. Another type of differencing we found to be helpful is looking at the actual changes to the 3D shape over time. This 3D differencing is useful in showing where there were changes in volume, both insertions or deletions to a particular model. The other type of differencing is video differencing or animation differencing, where we have multiple keyframes within a sequence, and each has maybe a different model state, a lighting state, changes in camera position and orientation, and we perform, in essence, a 2D comparison at those individual renderings for each individual frame or a subset of the individual frames within a given sequence. We come to a common theme in going through this differencing work, and the common theme is that these tests are repeatable. They can help ensure consistency. They're contained in a way that's very similar to unit testing perspective, and we felt that if we share these tests in glTF sample models and scripts out there, that we can help improve the testability and help address the problem of consistency between the renderers and the viewers. So the major conclusions of our work are that yes, we've found these differencing methods, and yes, they've helped us shake out a common recurring set of reasons why. So the first is, yay, we're able to test glTF 2.0 and X3D 4.0 and able to make those representations with a subset of models, the glTF 2.0 sample models. And then we know that most of the differences are caused by not having defaults in a particular scene, or differences in default lighting settings and things like that. They're not necessarily conversion errors, although we did find and update the X3D specification, so it has been quite helpful. So there are a number of areas that we came across for further work. The first is in the viewers and converters area. There are some issues with correctness that we identified that could be worked on and improved. The implementation of the spec, just various features that need to be built out. And then looking at sort of the spec itself in terms of color mode and making sure things are kind of fully correct there. On the efficiency side, there's work that's needed for binary encoding, as well as tools and implementations to bring about a more efficient representation, a binary representation of the models. Well, we're happy to help and to join the party to make Web 3D graphics better. We want to say thank you to the folks who have built the glTF 2.0 samples repository. That repository is very detailed and covering many of the specification topics that are useful when doing differencing testing. We feel that we can add more open test examples that will be even better. We think it's helpful to continue to convert glTF to X3D, not only for differencing comparison but for generating samples as well. We feel we can be a good partner in a continued dialogue to share the best ways to convert glTF to X3D. And we hope that we can liaison and work to match capabilities and learn from each other. We're very thankful that the Web3D Consortium and the Kronos organization have entered into a formal agreement to ensure that compatibility and correctness continue for these complementary standards. We'd also like to mention that none of this work would be possible without the deep technical expertise and sustained efforts of Michalis, Kamburelis. We're very grateful for his continuing work with both X3D and glTF. We are continuing to work on this effort. Please send us bug reports. Thank you.